Thanks for giving me the opportunity to present my work that I'm doing with Lorenzo Cironi at Columbia University. I'm going to speak about turbulence, but this time I'm going to focus more on an aspect that is maybe not touched deeply in the conference until now, that is the capability of turbulence in a highly magnetized environment to accelerate particles out of thermal equilibrium. So let me give you some brief motivations. And there are many objects of a different variety out there in astrophysics. I just put 3 of them here that are characterized by the high magnetization, pulsar wind nebula, active galactic nuclear jets, gamma ray burst, but many of the things that I'm going to discuss are applicable also to the sun and other environments. They show distinctive non-thermal broadband spectrum of radiation. They all have these kind of features. Here there are synchrotron and Compton spectrum coming from the pulsar wind nebula. Here this is the crab. Or for example, also blazar jets have also distinctive features in the spectrum of radiation. And here there is a bump coming from synchrotron, and this is inverse Compton. Gamma rays bars, same story. So how do we explain it? A natural thing to look is to look at turbulence. Why? Because these environments are likely to be turbulence. We are not directly there to measure the fields, but we can infer from the plasma parameters and some indirect measurement that they are turbulence. So it's a natural link to see what is the consequences of turbulence in accelerating particles. So the first thing that we want to address in this talk is if turbulence can produce a large fraction of non-thermal particles. And then the second question is, if this is the case, we want to understand how the non-thermal distribution of particles depends on the physical parameters of that regulate the problem. In this case, things like magnetization, turbulent fluctuations, the size of the system, of the largest eddies. And then the very last question will be, what are the physical mechanisms that regulate this process? These are the most important part in reality, because only if we understand the third point, then we can extrapolate our results for the astrophysical systems, because our simulation, of course, are limited by the size of the computation that we can do, and we cannot really direct apply the exact parameters that are proper of the astrophysical system. I'm not gonna cite any of these works. All what we have seen is published in these last works. So let's start. So the problem that we want to address is complex, nonlinear, multi-scale. Addressing that retaining the full complexity in an analytic way is unfeasible. So it's not a new problem. People have thought about it, and there are different ways to attack it. So the way that has been mostly used in the past is to run test particles on top of or synthetic turbulence prescribed in some analytic form, or MHD simulation of MHD turbulence where you run past particle on top of that. This has been the most common technique used in the past. Then more recently, hybrid simulations in which ions are kinetic and electrons are fluid. And in this way, you can capture the acceleration of the ions for first principle. And then there is another way that you just simulate in a fully kinetic way the entire system. Of course, it's more expensive, but retain all the physics that eventually we need to know. And since we are brave guys, we will take this last approach, the fully kinetic one. So what we have done is to perform fully kinetic simulations. So with the peak method, that just briefly, you're probably already aware, it's just practically having a large number of macroparticles that deposit current on a grid where the electromagnetic fields are solved through the Maxwell equations, then provide the Lorentz force that push the particle, and then the particle deposit the current, and the loop is closed self-consistently. We need to use a large number of particles, and it is complicated because we want to probe very large domain size. In this case, I'm going to present simulations that are all done with the code Tristan MP that has as Anatoly Spikoski in Princeton, the main developer. And they are all very large scale. They are all peak simulation that has about 2,500 cube cells. Why this? This is very important because I'm going to show a simulation that comes from kinetic, a peak description, but I'm going to make the system size so big that I'm going to capture also the MHD cascade. This is very important, and we will see later why. So some other details. All the simulations are in decaying turbulence. So there is a mean magnetic field in all the simulations that is on the Z direction. And there are initially some fluctuations in the form of galvanic fluctuations on top of it. And they will decay. And here is an example of the density fluctuations in the turbulence that result from these simulations. And you can see that the lengths of the cube are normalized by this small L, that is the energy carrying scale of the system. So you can imagine that are the size of the largest eddies of your simulation. And I'm going to focus in this parameter regime, that is the one relevant for the object that we have seen before, like the Crab Nebula, in which they are highly magnetized. By highly magnetized, it means that this sigma is much larger than 1. And this sigma practically is it represents the ratio between the magnetic energy density in the turbulent fluctuations divided by the relativistic enthalpy of the plasma. And so it means that it's much larger even than the rest mass energy density of the particles. So there is a lot of energy that can potentially be converted to the particles. Then the relativistic temperature is about 1. And the fluctuations for this simulation that I'm going to show, they have fluctuation in the magnetic field that are of the same order of the mean magnetic field at the outer scale. And I'm going to show you results for a pair plasma. We have already simulation for electron-ion plasma, but for this presentation, only I'm focused on the pair plasma case that is relevant for all the astrophysical objects that we have seen before, that in practical are active galactic nuclear jets, pulsar wind nebula, and probably also gamma ray bursts. So this is a snapshot. I want to show you soon an important feature of the simulation that you can find also in MHD. That this is the current density along the mean magnetic field, and this is, you can see that there are a lot of current sheets. This is one slice of the three-dimensional domain, and this is a video in which I'm going to show you fly through the turbulence domain. So now we are going to see how the current sheets are in the turbulent domain. You can see that there are plenty of current sheets. Some of them also break up inside. There are some kind of flux rope structures. We will see some soon later that there are these flux rope popping up in these current sheets. They are very important for the particle acceleration purpose, and then we will see how they enter into the game of the particle acceleration.
So when I look at that,
yeah.
You say flux rope, what should I see?
Yeah, let's see, even here, we have to, later it will be very clear, but there are these kind of bubbles sometimes. Yeah, the pointer, unfortunately, the light is not strong. But let's say this kind of, there are some kind of bubbles sometimes popping up. It is not too clear here because we have to zoom in some of the current sheet. Later I will show you a clear zoom that show these flux rope structures. Yeah, good point. Yeah.
What's the plasma beta here? It's high.
Oh yeah, it's very small because high sigma means small beta. So this is a high sigma regime, so it means that it's magnetically dominated. So beta is very, very small.
Okay. Do you have a picture of what this is?
No, not in this, but we can show it. Look at it later. Yeah.
Right. But I guess that just follows.
Oh yeah, definitely. Okay. So this is the spectrum that come out of this specific simulation, and you can see this is fully kinetic. You have, let's say, this is since turbulence is decaying, you can see that the fluctuations are decaying in time, and these vertical lines indicate where the time that correspond to the magnetic spectrum here. And you can see that there is an inertial range of the MHD scale, and then there is a steeper part when you hit the kinetic scale. In this case, is the electron skin depth. And you can see that this is kind of consistent with both like Goldrake-Schroeder or a little bit shallower. And then it becomes much steeper like k to the minus 4.3. There is not a clear theory for turbulence in that regime, but it is reproduced by also other groups, so it's it's safe. But the most important part here is not really on the slope, it's the fact that we have a clear MHD range in addition to the kinetic range. And we will see later that it's very important for accelerating particle that MHD regime. This is the outcome of this simulation. This is the particle energy distribution. It's our main interest in this talk. You can see this is a time evolution of the particle energy distribution. And at the beginning, it's a Maxwellian. But as turbulence evolves, you can see that the Maxwellian is heated and also developed a non-thermal tail. That for these parameters, is the non-thermal tail has a slope that is 2.9, but only for these parameters. Because if you increase the magnetization, here the inset showed that increase the magnetization, the slope become harder, so the power law slope become decrease. Yeah.
So you ran the suite of these simulations?
Yeah, I ran also a suite of simulations. Yeah. They were pretty expensive. Yeah. And at the same time, the high energy cutoff increase as the square root of the magnetization. That this comes simply from the fact that the high energy cutoff is given by the Larmor radius of the particle being of the same size of the largest eddies in the system. After they get to that size, then they are not anymore well confined and they cannot really get energy anymore. So the turbulence is also efficient in really boosting the particle to the maximum energy that they can eventually get. And this is a non-trivial statement because turbulence is decaying.
What is the maximum energy they can? What is this 10 to power 3 in kilo electron volts or whatever? What is the scale?
Oh, I don't know, depends on the mass here. These are all electrons. But this is, let's say...
How close they come to the speed of light?
Oh, they are practically the speed of light. But let me say this. We should not take these, I'm not trying to fit anything here. So we should not take this as a claim of this could be what happened in the crab or other things, because this size, the maximum the maximum energy is is proportional to the length of the eddies. The length of the eddies here is determined by the size of my simulation. If I want to simulate the crab, I have to make the simulation much bigger. So we have to focus on the physics. So I mean that this can be even 10 to the 9 if we make the system larger, and we can reproduce eventually, if we understand the physics well enough, what happened in the crab. So I mean, I don't know if I kind of answer, but yeah, but of course it's...
I'm wondering, I mean, it's totally...
They are relativistic particles, of course.
Because people are speaking of accelerating particles through plasma interaction instead of, going like at CERN. I was wondering whether turbulence could help in this effect.
Oh yeah, definitely. Even to higher energy than the CERN here.
So why don't they do that?
Of course, you need very strong magnetic fields, very large scales. Let's say you cannot, I do think, miniaturize the process within at the moment to the size of the CERN. Yeah. But the energy can be way larger. There are no limitations in this sense. So let me now focus on the most interesting part now, that is understanding what's going on, because that was just an outcome, the final result of the turbulence itself. So this is a video. It's a 2D video. This is the only 2D result that you are seeing, but because I'm claiming that this feature actually remain also in 3D. So I'm going to show you a video. This is the entire domain. There is still the current. This is a zoom, and this is one of the particles that become energized, that is going around. So I suggest you to pay attention to this part. And you can see this is the Lorentz factor of this particle. You can see that at a certain point, there is a sudden jump in energy. So here something should have happened. So let's pay attention to what happened there. This is just for one particle, but then we're going to look for some statistical measures. You can see that there are these plasmoids, these flux ropes right here, popping up here. And you can see that the particle were exactly in this current sheet, that is a reconnecting current sheet at that moment. I'm going to try to stop it at the right moment so that we can see it well. You can see there is this flux rope popping up in the current sheet. This is a reconnecting current sheet between two flux tubes. And the and since here there will be a parallel electric field that is not described by standard MHD, so you need, or at least you can, but you need the resistive MHD or a kinetic model. And you can see that here there is a sudden increase in energy, and then there is another increase in energy, but at a lower rate. Oh man. So I'm gonna show you 10 particles here. These are binned in such a way that they end up in different energy beams, and you can see that they are all characterized by the jump in energy. So let's see what happened better in this jump. This is a very, very important plot, I think. Maybe if you have to have one takeaway, this will be that one. These are the probability density function of the current felt by the particles, but with particles. The red one are the particles that get that jump in energy, while the blue one are the entire population of particles, both thermal, non-thermal, everyone. And you can see that there is a huge difference, because this one, as you would have expected, peaked at 0, then there is a tail that comes from intermittency, because they are actually sampling the entire domain. But this one is not peaked at 0, and it peaks a value of the of the current that is more than 2 times larger than the root mean square values that actually are current sheet, because it's a very high value of the current. And if we look at the space location, this is the region where the current exceeds this threshold, and this is where this acceleration is occurring. You can see that it's clustered in the current sheet. So let me briefly move. There was a question about the flux ropes. This is a zoom. For example, these are isosurfaces of the current that you see that come out of this current sheet, because people may argue, okay, you need to have an efficient process, but current sheets have a small filling fraction, so do they matter? These are reconnecting current sheet. So you have to imagine a reconnecting current sheet sucks plasma inside. So during their lifetime, they live for a certain lifetime, that is the nonlinear addition over time, the local one. And then there is a reconnection velocity, that is the reconnection rate times the speed of light. So if the reconnection rate is high, they can suck a lot of plasma. So this current sheet, during their lifetime, they can process a lot of plasma. And in one eddy turnover time, when one can compute that they are able to process the reconnection rate times the volume of the system. So if the reconnection rate is high, and typically many times is 0.1 in this business, in few eddy turnover time, they can inject a lot of particles for the subsequent acceleration. So this is another fly-through. But in this case, these show you the mean magnetic energy of the particles in the cells of the simulation. And you can see already now that many particles are energized in structures that are like current sheet structures, and they correlate with this current sheet. This is, of course, this is not individual particle. This is an average kinetic energy in the cells of the simulation. And you can see that they well map these current sheets. But I want to point out that this is not the entire story. So I don't want you to have the takeaway that, okay, turbulence produce current sheets, and so they reconnect and they accelerate particles. It's only the beginning of the story, because there is a second part that is this. You can see now, this is not anymore a log plot. Reconnection gives you the parallel electric field, but then there is the perpendicular electric field that comes from the turbulent fluctuation itself. So it's just ideal MHD. And you can see as a balance that at the beginning, all the gain, this is the work done by the parallel electric field, this is the perpendicular electric field, and this is the total energy gain normalized by mc squared. And you can see that at the beginning, everything is done by the parallel electric field, but then is the turbulent fluctuation, ideal MHD turbulent, that propels the particle to energy that can be as high as the simulation allow. This is one particle, of course, and this is the second plot that I'm proud of, that I think you should remember. This is the statistics for all the particles. Now there is no bias of selecting one particle of another. And this is the distribution function in terms of the energy and work done by the parallel electric field. And you can see that for all the particles, these are every slice you can think as a PDF. All the particles, when they have low energy, they are propelled by the parallel electric field. But after a while, after a certain degree of number of energy, value of energy, it flattens. So it means that if you want to see what will be the energy gain, if you want to propel a particle up to a Lorentz factor that is about 400, you cannot do it with the parallel electric field, because here you need to have some additional part. That this is the of course this is the perpendicular part, and you can extrapolate this also. Imagine, yeah. They are in the to-do list plan. In the sense, these we have done it with pair plasmas that are the easier way to go in the sense for computational reason. But we have already run can affect the acceleration only when particles are captured in regions where there is a strong parallel electric field. So they are typically localized region. But as soon as the particle armor radius start to be very large, it averages out these small scales, and then it's really ideal MHD with test particles on top of it that can describe correctly the physics. This is my actual understanding. So that after the initial energy gain, particles can be correctly described by ideal MHD interaction with test particles. At least this is what the simulation show.
And you also show the spectra.
Yeah.
Have you just do some comparison with observation, the photon synchrotron spectrum?
We are actually doing this for several objects. We are actually very involved in the crab because there is a very clear spectrum, and so we are doing that. This is the work that we are doing exactly these days.
Okay.
I know. Let's say I don't want to tweet any parameters because there were no free parameters here. The fact that you show a small power law, it's only because the kinetic simulation is small. It's like a very tiny fraction of your astrophysical system. If I can make the simulation much larger, the physics tells you that the particle can get more energy and they scale linearly with the system. So if you make the simulation twice larger, you will get twice larger power law. So it means that it's a tiny power law, but the tiny power law is just because we have done with a tiny computer. Of course, the computers were not tiny because they were 200,000 computers. But I mean, what we can do now on our supercomputer. But you should not be concerned about reproducing exactly the result, but understanding the physics that produced this result.
Okay, I think we can move on. So let's thank Luca again.
Thanks.
Okay, thank you. I'm going to talk about relativistic turbulence with fast radiative cooling. So first of all, what do I mean with that? So relativistic turbulence, I mean that I'm interested in system or magnetically dominated turbulence, as Luca was saying in the former talk. It's the same. It's the same thing. It's a regime where the magnetic energy density is much larger than the energy density associated with the mass of the particle. So then, since the motion is relativistic, turbulence is decaying typically on the light crossing time over the largest largest eddy. Third thing, since the magnetic energy density is so large, simply by the conservation of energy after the magnetic field has decayed, the typical electron Lorentz factor is much larger than unity. So this is the magnetization parameter that Luca was describing in the previous talk. So this is the regime that I'm interested in. Second, what do I mean with fast radiative cooling? So these electrons that are heated to such huge Lorentz factors will radiate away their energy, and typically electrons lose their energy faster. The more energetic is the electron, the faster the energy loss is. So with fast radiative cooling, I mean that the typical time scale over which these electrons lose their energy is much smaller than the light crossing time over the largest eddy. So this is what I mean. So where is this regime? Where this regime might be important? This regime might be important, I think, not only, but for sure in jets from active galactic nuclei. So here is two very famous pictures. On the left, M87, on the right, Centaurus A. These are, so what is active galactic nucleus? Active galactic nucleus is the central region of the galaxy where the luminosity is where most of the luminosity is thought to be. It's very luminous, and most of the luminosity is thought to be coming from an accreting supermassive black hole that is sitting there. Some of these active galactic nuclei, as these two examples that I'm showing here, also manage to launch relativistic jets, and we think what's happening in these relativistic jets might be well described by turbulence, where cooling is very important. The jets are thought to be magnetically dominated, so relativistic turbulence, and are thought to be very efficient radiators, so fast cooling. So if I'm interested in studying what's happening in the jet, what is the object? What is the objects that I should look at? So I should look at these blazars. So blazars are AGNs with a jet, and the jet is pointing in the direction of the observer. So since the matter in the jet is so relativistic, if the jet is pointing towards me, the radiation that is coming from this matter, the radiation that is irradiated from the jet, has a very strong Doppler boosting, like an ambulance which is coming towards me. So radiation from the jet is outshining all the other components that one can see in these cartoons. There are many, but if I look to these objects where the jet is pointing towards me, I basically can study almost only what's happening in the jet. So if I'm interested in the jet, these are the objects. These blazars are the objects that I should look at. In this plot, I show the spectral energy distribution, 4 examples of typical spectral energy distributions of these objects. Spectral energy distribution is the amount of energy that is radiated at every frequency. One can see 2 things. First thing that one can see is that the radiation is clearly non-thermal, and the spectrum has 2 bumps. So what we think is that these 2 peaks, these 2 bumps in the spectrum, 1 and 2, are produced by the same population of electrons by 2 different emission mechanisms. This first peak is thought to be synchrotron radiation. Synchrotron radiation is produced when an electron is gyrating in a magnetic field, it's radiating its energy, and this radiation is what we think that we are seeing here. The second peak is thought to be inverse Compton radiation. Inverse Compton photons are photons that gain a lot of energy while scattering a relativistic electron. So I have a photon that is not that much energetic, a very energetic electron. There is scattering. The photon gains a lot of energy by this process, and this we think that's what is producing the second peak. So this is the objects that I'm looking at. So in order to reproduce this broad non-thermal spectrum, phenomenologically, what we need is a broken power law energy distribution for the electrons. So why broken power law? The shallower part of the power law is what is producing the rising part of the spectrum. Then I have the electrons at this break, which are radiating by synchrotron, which are radiating at this peak when they radiate by synchrotron, and that they are producing also the peak at the inverse Compton. And then I have the steeper part of the power law, which corresponds to the declining part of the spectrum. So this is what I need. Observationally, this is what we need. So the question is, can this power law electron energy distribution be produced by relativistic turbulence with a fast radiative cooling? I think the answer to this question is yes. And the main reason is the way electrons are heated by turbulence. As we were seeing in the previous talk, so here I show recent simulations by Commisso and Sironi. In this top panel, I show the typical, I show few examples of the evolution of the Lorentz factor of a particle versus time. So as one can see, all these particles experience a sudden jump in energy, and basically all the available energy, these electrons are gaining all the available energy in just one event while they are passing through one of these current sheets. So all the available energy is this magnetization parameter that I was defining in the beginning, and it's much, much larger than unity if turbulence is magnetically dominated or relativistic. The second important point is the time scale over which this is happening. This heating is almost impulsive. Means that if I estimate this time scale is just the momentum. So in this current sheet, what is accelerating the electrons is an electric field of the same order of the magnetic field. So if I want to estimate this heating timescale, I just take the final momentum and I divide by the charge of the electrons times the electric field or magnetic field. They are comparable. This timescale for typical astrophysical system is very, very short. The important point is that the outer scale, the scale of the largest eddy, this one, is not appearing here. So what I'm saying that I think in these large-scale astrophysical systems, it's very important that this heating timescale and this dynamical timescale are very well separated. So in the beginning, I was saying I'm interested in systems with a fast radiative cooling, means that the cooling time is much faster than this dynamical time. But I think the crucial point is that for reasonable astrophysical parameters, this scale is so large that this heating time is much shorter than both this and this. So there is this very large separation of scale. What does it mean? It means that since this heating time is so short with respect to the cooling time, cooling is basically ineffective during this injection phase. So during this injection phase, for a reasonable cooling prescription that I have in astrophysical objects, cooling doesn't do anything in this phase. So what happens? It happens that these simulations are all without cooling, but if I think what may happen if there is cooling. So the electron is heated. During this phase is so fast that the cooling doesn't do anything. And then this electron is heated up and then starts losing energy due to cooling. And it loses energy fast. I mean, it loses all its energy by the dynamical time. Then I have another electron. It's heated at a different time and then it loses its energy. And then another electron which does the same. So if I ask at a given time, what's the electron energy distribution that I see? There are two crucial points that I was already mentioning. So first point is that the cooling is ineffective during injection. Second point is that these injection events are almost uniformly distributed over the dynamical time. So what I expect to see eventually, if I'm interested to the number of electrons at an energy which is here, lower than this gamma heat, the number of electrons that I'm expecting to see at that energy is proportional to the time that the electron will be losing its energy. So the number of electrons I see at this energy is proportional to the time that the electrons is spending at this energy. This time is what I was defining as a cooling time. So since for synchrotron and inverse Compton processes, this cooling time is proportional to gamma to -1, this is a very well-known fact. What I expect eventually is that over this range, at Lorentz factor smaller than this injection Lorentz factor, I expect to see a distribution which is the n over d gamma proportional to gamma to -2. So this very fast heating allows one to have a power law energy distribution over a wide range of extending over a wide range of Lorentz factor. So this is much larger than 1. So how does this compare with observations of blazars? I would say pretty well. So this is simply phenomenological fit. This N1 is the power law index below the break. This N2 is above the break. So as one can see, basically all the objects are consistent with the power law energy distribution, the n d gamma proportional to gamma to -2 at low energies. So I would say that this turbulence with fast cooling is very promising to explain spectrum of blazars. And one, of course, so at gamma smaller than this gamma heat, one expects this distribution, and then the distribution is expected to steepen very fast, very, very abruptly above at energy higher than this one, because basically injection is ineffective at energy which are here. So if I go to energy above this one, I expect to see basically no particles. Yes?
Yeah, sorry. I'm just trying to understand the physical picture. Here, the turbulence that you're describing with cooling, is it happening along the jet or in the accretion?
Along the jet. So yeah, let's say that I imagine that the emission region is like a spherical blob with some turbulent magnetic field. The magnetic field is decaying, and it accelerates particles, and these particles are radiating, so along the jet. Yeah. So this distribution is consistent with the observed spectrum, and I expect at energy larger than this one, the distribution to become steeper. So again, this is again the broken power law. This is the gamma 2 minus 2 part. This is the steepening. This is what I expect for this thick line, is what I expect for the break of the distribution. In the fast cooling regime, when the electrons, this gamma heat cool faster, I expect this break to be exactly at this gamma heat, so at the magnetic. So I expect this to mark to be the magnetization of the initial magnetization of the jet. In this regime, cooling becomes very small, so I expect this break to probe the Lorentz factor of the electrons which are cooling. This regime is basically important for astrophysical systems. So this is what these observations of blazars, and I see indeed such trend. I see that the break that I need to fit the data is basically proportional to the Lorentz factor of the electrons that cool within a dynamical time if this gamma cool is large, and then it flattens here, as I was expecting based on turbulence. So I think the way to interpret this is that this flattening is basically telling us what is the magnetization of the jet. So I think this is telling us that most of these blazars in this study are consistent with having an initial magnetization in the jet before the magnetic fields are decaying of the order of 100. So these are finally my conclusions. I think a very important point for turbulence in astrophysical systems is that this heating timescale is much shorter than dynamical time. And this is what allows us to, I think this is what is allowing to produce a power law electron energy distribution, a non-thermal with this characteristic -2 spectral index. This is at low energies, and I think this is promising to explain radiation that we see from these objects, in particular these blazars and AGN jets in general.
Questions?
So, I mean, what do you mean to test these pictures? I mean, so I think one important point is that here. So you should have an acceleration mechanism which produces a spectrum which is basically the ND gamma 2 minus 2 at low energy, and the ND gamma 2 minus, I don't know, 3 to 5 at high energy. I think there is two important points here. One important point is that the spectrum, this is not extremely robust because there are very large uncertainties in the data. But let's say I have a universal observation, and I see that I need something like a universal electron energy distribution at low energy, and then non-universal electron energy distribution at high energy. And this is steepening a lot. So I think this is one important thing to explain. I think, I don't know, I didn't yet run any simulation. This was just order of magnitude estimates. One can see if indeed, if one puts in particle in cell simulations, one puts radiative cooling, if one indeed finds something like this, I think it's possible. So this is one way. Fitting exactly the spectrum, I think is hard. I mean, one can see two bumps, but trying to fit individual objects, I think is a bit too early. I mean, I would rather try to understand some basic physics which is going on, and then try to have some motivated prescription for them making my fits to the objects. But yeah, this is what I
Really nice work. I'm curious to know at what point does the viewing angle
why do you expect that the viewing angle?
Well, you're considering the particular geometry of a blade.
Yeah, more or less.
Jet, so
Yeah, but if you change the viewing angle, you just shift. I mean, you shift. Oops. Where is it? Here. If you change the viewing angle, so there is this Doppler factor. If you change the viewing angle, you just take this. More or less, you shift the spectrum at lower frequencies and then lower luminosities. So I don't think the spectrum is changing that much. It's simply more difficult to observe if you change the viewing angle because you shift at lower luminosity, so it's difficult to see something. And it's more difficult to have a clean system because then you start seeing, I don't know, something related to the accretion disk, other stuff, which here it's more or less you don't see anything. If it starts covering part of the spectrum, already the data is not perfect, so it becomes more and more difficult to say something.
Judging from this plot and looking at the error, I didn't see the error bar in that table. If you the table that you showed, but here there's an error bar here.
Yeah.
And I think at the high frequency side, error bar is a little bit larger. I think your determination of this low frequency side looks pretty good. With the error bar, it's pretty small, but as you go to higher frequency, it's not as good. If you were to assign the error bar on this -2 to -4 index, like this breaking power law, are there really systematic changes from system to system, or are they actually consistent with the single power law?
I agree. So error bars are very large. I have to say here I decided to put this talk because this plot because it was showing many spectra at the same time. The way they constructed this plot was taking all the objects that they had in a range of luminosities. They stuck the spectra all together and they constructed some average spectrum for all the objects in this luminosity bin. So of course here we have, let's say, the blue line corresponds to many objects. Some of them have a spectrum which is reasonably well constrained. Some of them have a spectrum which is not well constrained. For the reasonably well constrained one, we can say more robustly what the two slopes of the electrons here and here are. For the worst constrained one, we cannot say much. So it's kind of.
If you take the best measurements, do you see systematic changes in the P1, P2 from system to system? Are they real, or is the data consistent with a single power law?
P1 is consistent would be the same. At least this is what people who does this fit say. P2. Difficult to say. Let's say that we need something which is very steep, and we need something which is so. If I'm injecting something with gamma to -2 spectrum, and I have a cooling break here in between, I expect the spectral index to steepen by 1 as an effect of synchrotron. So I would say that it's quite robust, the fact that the steepening is more than 1. So this is quite robust. Then the exact determination of what the spectral index is here, I agree with you that with most of the objects is very tough.
Yeah, so in fact, I think both P1, P2 are quite steep, I mean, compared to like GRB and possibly Nebula. In that case, they have this like more like -1 instead of -2.
So for pulsar with nebula, I have here it's much steeper. Yes, I agree.
No, I mean it's much harder. Yes.
This is for pulsar with nebula in the radio. I need it to be flatter.
Yes,
I need gamma to instead of gamma to -2, maybe I need gamma to -1.4 or something like this. Yes, for GRBs, I think it depends which frequencies you are looking at.
The prompt emission, the people use the band function, and that is also around -1.
Yes, I don't know. I'm not.
I think it's probably different mechanism.
With pulsar with nebula, it's not. I mean, with pulsar with nebula, I think the radio for sure the radio spectrum of pulsar with nebula is not due to cooling. I mean, if you take the spectrum of the crab and you take the dynamical time for the lifetime of the system, like 1,000 years, you have that the electrons at the peak of this that are emitting at the synchrotron peak are cooling within a dynamical time. So I would expect no. I would expect here in this object I'm claiming that these electrons are cooling in the dynamical time. In the crab, it's these electrons which are cooling in the dynamical time. So I would say no, there is no reason in the crab to be gamma 2 minus 2 in this range. It's something different.
Yeah, so it sounds like there is overall.
In the in gamma ray bursts, I would say that I don't know. I was reading some recent work. They try to fit the spectrum with broken power law. They say that there might be the peak, then a gamma 2 minus 2 electron distribution, and then nothing. And the very steep part they claim to be like simply nu f nu proportional to nu to the 4/3, which is what you expect below the minimum for synchrotron radiation. This is what they were claiming, but I'm not that much into this. So,
If no more, okay. Oh, okay. We did. Yeah, let's thank the speaker again. Yeah, and all the speakers in the morning.
Okay, should we get started? So we wanted to do a final discussion, and we had a couple different ideas of how this could go. One being maybe breakouts, but we decided that because it seems that the energy that was injected on Monday is now rapidly dissipating. we thought maybe it would be nice to just do a group discussion, still with the discussion topics that some of you submitted. Yeah, and so the first thing I wanted to address is this picture here, which was produced by your submissions to the questionnaire website question that I sent out. So I did this morning, so I think we could maybe improve on the visualization a bit. But basically, these are the main words that about 25 of you submitted as to the question of what is turbulence? How would you define turbulence? And so you'll see a lot of these words are just repeating because I wanted to fill in the space of the Flatiron logo. But a lot of words pop out that maybe we could expect, one being multi-scale, another being cascade, energy transfer, stochastic. At least two people wrote swirly, which is fantastic. Yeah, so chaos also appeared several times. So this is fun. I'll maybe improve upon this image a little bit and then send it out by email to everyone in case you want to look at it further. But thank you for those submissions. This is really fun. You can still add, actually, yeah. Please, if you didn't submit your definition, please go. And like I said, I think I'll play with this a little more. So if it's not too late, so submit and then I'll add in additional words. So if you think of words that should be here that aren't on here, then add them and they'll pop up. Oh.
How many words do you know?
Yeah. Okay, so this is just a screenshot literally from my Google Doc, which was sent out to the invited speakers. And then we had an additional number 6. This one was from Boris. So Boris, this is your suggestion for a discussion on anisotropic turbulence. I wanted to address maybe one aspect of something that we can all, whether we're in biology or physics or astronomy, get behind, which is all these different statistical tools that have come up throughout the meeting, and potentially that would be a very nice basis for collaboration, actually, between all of us in these different disciplines. And then we had several other suggestions by our invited speakers, and several of them are in the room, so maybe they could lead in part the discussion topic that they were raising. And then Mike probably has some additions as well.
So I just want to make a couple of remarks that bear on. Actually, I just have a question. I mean, hold it to my mouth. Yeah, okay. I just have a quick question, just because of Sandra's talk this morning, and then learning about the Parker spiral. Does the Parker spiral exert a hoop stress on the sun? Kind of? Yeah, I'm imagining that the sun is the little pole in the viscoelastic fluid, and you're wrapping up the magnetic field lines, and it's okay. So that makes sense as a question, I guess. Okay. Now, I did have a couple of other remarks. I did just want to say that for those of us that are working in the biological problems and things are being called turbulence, I don't think we need to invent a new word. I think, to substitutes, perhaps there's not cascade mechanisms in all of these problems and all of that, but there's a set of phenomena there that I think are well labeled as turbulence, and we should just make sure we put the right adjectives in front to discriminate between the varieties of turbulence, as Sriram refers to. The other, I thought, if we get to that about the varieties of turbulence in active fluids, I think it's maybe worth talking a little bit about whether there are some very strong analogs, not just kind of this is kind of like that, but are there some really strong kind of mathematical structural analogs between some of these systems? And I think that there are, maybe not the ones that we talked about, actually. And I did want to say I hope we talk some about these first three in particular. And I really enjoyed some of the machine learning talks. I mean, given in kind of my little editorial comment before I turn it back to this is this: I thought that properly constrained, properly posed, to look like my mind was kind of shifted a bit, that it could be very, very useful in some of the things that we look at. So that was it. So.
Right. So I will start with the first point. So interdisciplinary turbulence diagnostic tools. So I put up this one slide on that point. And this is sort of going back to Monday, where we talked a little bit about different diagnostic tools. And then as we saw throughout the week, people tend to use things like structure functions, correlation functions, energy spectra, PDFs. We also saw some topology tools popping up during the week. And then there was also some discussion of triads, right? So 3-point type functions also being used in this field. And I think this is fantastic, and this is exactly where a lot of us can find common ground. In terms of open source software, there's at least these different diagnostic tools that I've listed here. When you go to this GitHub account, which is hosted from Eric Koch, and he did all the main development work for these tools, this is primarily for astrophysical applications. So when you go there, you'll see that these tools are very much developed for that very purpose. However, I think all of these statistics are extremely generalizable to various problems, right? So things like, for example, a genus statistic. A genus statistic is a topological measure that will tell you if your topology is mostly clumpy or more like a Swiss cheese versus like a meatball topology, right? And topology like that can be applied to many different problems, right? So not just astrophysics. And so I wanted to maybe ask all of you if there was a particular statistical application that you saw from a field outside of your expertise that now you're thinking, oh, this would be actually really interesting for my my problems that I'm working on. If anyone else had that feeling this week. So personally, I'm actually excited to revisit things like bispectrum, having seen bispectrum applied in atmospheric applications, like similar to like what Boris was talking about in his talk. So this is something I think that I'm going to take home and apply in my own simulations. Did anyone else have some, machine learning we'll get to. I think that I put that as a separate topic.
So on the genus tool, so I thought that someone should have been provoked by Zonomir Dojic's talk. For example, when one is looking at all the kinds of defect structures that form in 3 dimensions, and he talked a bit about how you characterize those, and they're very topological in flavor necessarily. So that would be
James, push your seat mic. Also, if anyone on the Zoom wants to participate in the discussion, that would be fantastic too.
Actually, related to topology, one of the tools that wasn't mentioned in the workshop is persistent homology. That I think it's a very new tool. It's not clear how much it can help, but it looks very promising. So that's one of the tools we should look at. I can show you if you want to. Description is so homology is a branch of topology that focuses on basically multidimensional holes, and you're using the tool to describe topological shape of data. So that such a tool runs across all these different fields, biology, condensed matter, turbulence, or what have you. Do I want to say anything more? It's a way that the way it characterizes shape is it gives you a tally of the number of disconnected parts, number of, let's say, closed loops, or three-dimensional voids, up to whatever dimension you think.
What does persistent mean?
Persistence is
like some sort of structural stability.
yeah, it's scale invariant. That's basically what it is. So the way you do homology computationally is you have a scale parameter that is used to construct a grid on your data. In topology, we would say simplex. And that simplex will allow you to do algebra on the data, and the algebra is what allows you to do the whole counting.
How is it related to turbulence?
So good question. So traditionally, I think our tools, you can break it down roughly into statistical tools or spectral tools. Right? We're either working with moments or spectra. Those are what I would call global tools. If you want to, let's say, ask questions like, how many vortex tubes exist in my computed field or observed field, you would want to use a tool like homology.
Yeah, and I think the reason why you want to look at these different statistical tools or spectral tools for the problem of turbulence, one of the defining characteristics I think that everyone can get behind is that while turbulence can look chaotic, right? You can see these chaotic motions. If you spatially or temporally average things like a spectrum, you see nice, beautiful, somewhat predictable types of behaviors in these statistics. So the order in the chaotic flow starts to appear when you look at it in a statistical sense. And that's, I think, why these statistics can connect all of us in these different fields.
Part of the missing word, correlation.
I think correlation appeared. Yeah.
It's up there.
It's.
I don't know.
On the word.
Oh well, you submit your words, please, and I will add them in. It's not too late. Xiao.
So I want to say something about plasma physics and astrophysics. They are quite closely related when we're studying astrophysical problems, and also solar physics and heliosphere space. So I think it's really big progress that we can see from Lucas' talk that they show that using peak simulation to simulate MHD regime. I think this is really a big progress, big development. But to make sure that it is really turbulence that we talk about, MHD regime, it would be very useful to apply these tools which are well developed in MHD simulations to peak simulations to fully study that, and then maybe it's possible to bridge the gap between MHD and PEAK to studying a broad range of problems.
And I think that's one thing that's so inspiring by the simulations Luca showed, because the simulations seem to finally be able to begin to resolve the inertial range. So I don't know if you want to comment on this, but I was just really impressed with these simulations.
Let me point out that that was a specific regime that was more easy to simulate because it was would be called like relativistic turbulence, such that the event speed become actually the speed of light. So, but we are entering now in a decade where we can actually attack that problem, and it will be useful actually exactly to compare with these statistical tools, all of them, eventually even more if someone can come up with some clever idea on some others to add to see if there are differences and where there are differences. I suspect that actually PEAK will behave much like really MHD on large scales.
And look, I have a question that if we are already, you are already in the MHD region, is it possible to just use MHD simulations instead of PEAK for studying higher energy particle acceleration?
Oh, that is a very good point, because actually will be maybe one of the main practical takeaway. If you want to simulate a large-scale system and you don't want to rely on microphysics because that will be a bottleneck, and then you can and you have an idea to tackle some kind of questions like particle distribution, you may exactly run MHD simulation and add particles on top of it and have a very, very reliable answer in terms of simulating a large-scale system. So this would be my way to go.
Yeah, that would be really good.
Yeah, I think I'm coming more from the cosmology side of things, and in cosmology we have this very nonlinear density, large-scale nonlinear structure that we would like to also characterize using many of these techniques. So I think there are many of these things that we see here is very common. Especially we use.
I would just add, actually, in the development of a lot of these, we borrowed them from cosmology, right? Non-Gaussian
Yes,
statistics like bispectrum, right?
Yes,
That's
yes.
yeah.
So I should, I like to say I've seen a development over the decade or so where I think one of the dominant prescription was endpoint correlation function, not just one, two, and three, and then higher order point correlation function. The Fourier transform of that would be power spectrum, bispectrum, trispectrum, and so forth. They're all higher order the Fourier component aspect of those higher order correlation functions. So that's probably should be considered eventually in the future, especially if you're going into a very nonlinear regime. In a way of characterizing cosmic web in large scale structure, I think we actually have attempted persistent homology recently as a part of the topological data analysis, and we were able to detect like the differences in cosmological structure formation due to things like neutrino mass. If you have a universe with and without neutrino mass, you see differences in those statistics, especially in persistent homology. So that was very interesting because that was a statistics that was never used to detect such as faint features to discover things like neutrino mass. So that was kind of successful actually. It just came out, the results from last year. And then maybe one thing I have not seen, but it's been discussed in the context of describing the gravitational lensing effect to describe mass distribution universe, is a Minkowski functional. It's just yet another way of characterizing the nonlinear structure in a different way than endpoint functions. So that's been explored in gravitational lensing world, and maybe that's something that we could add in as yet another statistics that we can consider.
Yeah, I guess one thing I a little bit struggle with is that in cosmology, there's nice analytic predictions for how all of these higher order statistics should behave. And that's not the case in turbulence, right? We don't have that many analytic benchmarks for higher order type, correlation functions. So I think that's an area that would be really great to see some more progress on, but I think not so easy.
The way that happened was to develop this perturbation theory, because the fluctuation was small and you can do perturbative approximation to these nonlinear equations and then just keep higher and higher order moments that allows us to model those higher order correlation functions, and then eventually try to reproduce the results of numerical simulations. So that was the effort going on between perturbation theory versus direct simulations, and they're trying to look for the scales where you can get an agreement, and that still continues. And as you go to deeper and deeper into nonlinear regime, the perturbation theory struggles, and so that was the very interesting development in cosmology over the past decade or so.
That's right. So, I think we have still several more topics, and can maybe turn the floor to number 2, which is somewhat similar to statistics, but really this is more regards to specific class of statistics, machine learning. So,
ashamed because thank you. I really didn't. I didn't realize that I was supposed to put that. But anyway, I will try to make up. On the spot, I will improvise. I have just one single point. I heard a lot of very beautiful talk on turbulence and how to model turbulence modeling, how to model the Reynolds stress tensor. I think I would like to emphasize what I already said during my talk, namely that since there cannot be scale separation on any simulation, it would be helpful. It's really my fault. Can I use? I don't have a blackboard, right? I should have put up 2 slides. I just didn't realize that I was supposed to. Anyway, again, if you have a finite, as you always have, resolution in your simulation, the largest eddy that you discard is basically equal to the smallest eddy that you keep, right? And these 2 eddies are bound to interact strongly, so there is no way their interaction can be described through the notion of eddy viscosity. And my point is that there should be a shift in the focus from eddy viscosity to eddy relaxation. They are the same as long as turbulence is close to equilibrium, which is never the case when you have boundaries. I'm not sure this is relevant to your community. I didn't seem to get the feeling that boundaries are a problem for you. Good for you, because
sometimes they are, but sometimes we cheat and we have periodic boundaries. So.
Okay, that's what we do in DNS. But when I mean, to me, turbulence, I was really fascinated. Thank you so much for this workshop. When I hear that turbulence is relevant to planet formation, to galaxy formation, my heart is I just could cry out of emotion. But to me, when I did it, turbulence was about designing cars, designing airplanes, and I promise their geometry is really calling the shots. Nevertheless, I think that shifting from eddy viscosity to eddy relaxation is going to be productive anyway. Now, that means that instead of instructing the machine to learn a static correlation between the Reynolds stress tensor and the tensor that it can resolve, there was a beautiful talk yesterday morning by Zanna, okay, beautiful talk. But I think you should try to see how machine could learn the mechanisms which activate memory and correlation in turbulence, because the main problem in turbulence is that what happens here now depends on what happened somewhere else then. And there is no way you can capture this fundamental mechanism if you insist on I don't know whether you are familiar with their rheological constitutive relation. Specifying the Reynolds stress tensor as a function of the tensor which I can resolve in the same point and the same instant of time is never going to succeed in describing this memory mechanism. And during my talk, I presented the one possible way of accounting for this, which is going to a kinetic formulation of turbulence. Of course, I didn't have time for detail. I think from a numerical point of view, this is a very convenient framework, but there might be others. There might be some smart Monte Carlo. Any good method to solve kinetic-like equation is mostly welcome within this program. So that's basically all I have to say. And what else? Yeah, the point is, well, which I would like still to make is maybe it's not obvious to everybody that viscosity there is nothing like viscosity in the kinetic world. Viscosity is an emergent problem, whereas relaxation is a fundamental mechanism. And the two only coincide when turbulence is in equilibrium. In equilibrium means that the large eddies are surrounded by small eddies, and they are just performing a sort of Brownian motion like molecules do. But turbulence has a continuous spectrum, so that is not true in general, and especially close to walls where even the large eddies are out of equilibrium. Now, whether this happens in your problems, frankly speaking, I don't know, but I think it would be interesting, and there's certainly a lot to learn in trying to see whether machine can learn dynamic constitutive relations instead of static ones. So that's all I have to say.
David?
What's been done with measurements in the simulations of unequal time correlators? Because that's what you need when you have memory. And the hope with things like machine learning is if the relationships between the unequal time correlators and what the Reynolds stress tensor is doing at the moment is in some low dimensional space.
That's right.
You might hope to learn that information.
Absolutely, I think so. I'm really not up to date, but I know for sure, and I was myself part of it. There has been a lot of work done in structure function, which has a measure of correlation in space. Okay.
But not in structure functions are usually written instantaneously.
Right.
Not unequal time.
Yeah. I think people who do atmospheric turbulence and they track passive species in turbulence, I think they have done work in time, in correlating two-point correlators in time for the particle trajectories. If you wish, I have a couple of names of people who are really working on that as we speak, professionally in the field.
I just had a small comment to that. Certainly, in the matter of structure functions, equal time as well as time-displaced structure functions are measured. At least my colleague Rahul Pandit, for instance, works a great deal on dynamic multiscaling, for example. So at least at the level of numerical measurement, it's certainly very much there.
But as far as I know, Rahul does all the time direct numerical simulation.
Exactly.
Which is, of course, useful to validate
that's what I said,
machine learning.
It's indeed only numerical studies. I don't know what analytical theories of it,
but that could be useful, to,
right?
Yes. For machine learning.
Right. Yeah.
Yes.
So also for our simulations of turbulence in disks, so which are vertically stratified, and we have ugly grids, so they were usually using then autocorrelation functions. So just take one point and then do what are the fluctuations in time and see what happens there. So this is much easier than trying to straighten out your horrible grid. So
sorry, I missed the point. What?
So this is then basically time autocorrelation functions, yes, where time is the function, and then getting out for one specific point what is then the typical correlation time for turbulence. So there you're really then analyzing time series.
Yes.
So still on the topic of machine learning, so maybe David, do you want to also join the party down here? It's an informal discussion.
Okay, yeah, I don't have anything fancy, so most of what I'm going to say is going to be a bunch of disjointed thoughts on this topic, because partly I think it's, maybe you saw from my talk on Monday if you were there, that it's basically unexplored, these unsupervised machine learning approaches to turbulence. So I just thought maybe to bring up a couple ideas about what might be on the horizon there. So as we know, we saw, in particular, Lara's talk was fantastic on using supervised methods to learn closure models for turbulence. And I'd also mentioned in my talk that this is one of the big areas of turbulence research for the turbulence modeling. And I think it's already having a big impact in that field. The next question, though, is that it's hard to sometimes get turbulence data, right? I mean, maybe you have 15 terabyte data set, but it's one Reynolds number. And so to actually learn anything, we want to go beyond that. And so, you need more than one data point. Now, unsupervised algorithms might allow you to somehow mine that 15 terabyte data set and learn some kind of structure in the turbulence that maybe humans missed. right? And one thing I'm thinking about in particular, actually James basically already mentioned it, which is topological data analysis, which is, I think, pretty much not applied to real turbulence simulations yet. It's on my reading list. I don't know much about topological data analysis. You must know a lot more than I do, but trying to go through and kind of learn clusters in the data, how things are related. And then in particular, I was thinking about things like relating whatever's learned there to exact coherent states, or even constraining your algorithms with some of these physics relevant parameter quantities like exact coherent states, which we believe are dynamically relevant for evolution of the turbulence. Now, none of that actually says anything about how one might actually do that in an algorithm, but it does touch on this idea of somehow combining unsupervised machine learning algorithms with physics-embedded machine learning algorithms, which for sure is the way to go forward. You have to embed the physics inside. Right? That also touches on what Sara was saying, too. I mean, you could imagine with these memory effects conceiving of some kind of spatially recurrent neural network, right, like an LSTM, which gets the memory effects instead of just fitting some fractional model, which, you know.
I think there is maybe not even need for that, because, I mean, not that I want to push the kinetic point of view too far, but again, let me stress the fact that if you approach the turbulence model from the kinetic point of view, your formalism remains completely local, because what the memory mechanism is embedded in the equation of motion of the relaxation time. And then if the machine learns this equation of motion, you're done.
Right.
You see what I mean? So
Yeah.
maybe we don't need more sophisticated networks than we presently use.
Right, you're just suggesting do it in the.
You change the
space.
target,
Yeah,
not the
understood.
structure.
Yeah.
I mean, as you know, I know little, next to nothing about neural network. All I know, I learned from you in.
Which is not much anyway. Sorry.
No. But
Yeah.
still, I insist that the fact of shifting the focus from viscosity, namely use something in the context of a fluid dynamic representation, to a phase-space representation, yet very simplified, might relieve you from the need of making of sophisticated neural networks, because the physics in configuration space is non-local, but in phase space is local. That's the point.
Yeah.
Non-local in 3D is local in phase space. That is the simple trick.
Yeah. Right. Yeah. So I don't know if people have other thoughts on that. I don't want to take everyone's time. Go ahead. Yeah.
I feel that the ways to add these conservation laws is very important in this cosmological hydrodynamic simulations that I have been involved in. We have two very famous code, SPH technique versus grid-based technique. And when you run simulations, there are differences that plagued our interpretation for decades. And especially because, for example, things like SPH code has this artificial viscosity, which prohibits the generation of it. Just not very good at like capturing shocks and generations of turbulence that results from that. At the end of the day, that basically it was the result of entropy not conserving.
Right.
That was not so. If you impose the entropy conserving scheme on SPH, then it improves better. It starts to agree better with grid-based techniques and so forth. That was like almost like a decade of work and discussions within the field to try to reach that state. That now we have this entropy conserving SPH code that people use. That we like, and then we could be more. We can interpret the results and so forth. I think we have a similar problem in vortex conservation, which is often not conserved. It's very diffusive. So there is a way of developing a vortex conserving scheme for hydrodynamics that allows us to actually do probably a better job in capturing the development of turbulence and vortex generations in its evolution. That's not done, I don't think, properly in most of the hydrodynamics, unless you specifically conserve some of those things. So I think these are the areas that I think that we could improve with something like machine learning if we explicitly conserve important conservation laws for a particular problem that we have in mind. We can't put everything in because then that's an over-constrained problem. But I think if you know, for depending on what regime that you're working in, which conservation law must be preserved for kinds of problem that you're working. I think I think it's probably one of the ways to go forward. I think it gives us a new technique.
Yeah, I think this is a nice point because we trust the equations, right? We trust that, you know, we're not, but we don't trust our simulations, right? Because of these boundary effects and all of these other potential numerical dissipation, numerical problems. So how to go from just training the neural networks on here's a snapshot of my simulation to, okay, here's a snapshot of my simulation, now do something with the physics informed. It's going to be an interesting step to take. Ethan, yeah.
Okay, I just wanted to make a brief comment there. Vorticity, for example, you can write down an equation and it looks like a conserved quantity, but in a turbulent cascade, it diffuses not because of numerical effects, but because the turbulence erodes it. So you have to be very careful how you write your invariant preserving codes, or you'll end up conserving things that you don't want to conserve in a realistic turbulent situation.
Yeah, so along all these lines, I mean, in you know, numerical methods with MHD and incompressible hydrodynamics, you have, you know, your div U, div B have to be 0, and as you all well know, you have, it's even a current topic of research how we can have our numerical methods conserve those exactly. They have these divergence cleaning schemes and all this stuff, right? And people are working really hard on that, and there's papers still coming out on it. People come up with physics mimetic basis functions, which I think is a really cool area of trying to make sure that whatever your numerical method is doing, it's going to actually just mathematically conserve the structure of the physics. But you could imagine, I don't know how to do this, you could imagine doing something similar with a neural net, where you have your activation functions, which are roughly like your basis. And right now we just kind of randomly choose some things because they worked well in the imaging community. But maybe you could actually imagine doing, I mean, people have done some radio basis function, neural network type stuff in the past as well. So that could be one way to go. But for sure, you have to, you know, your sun, there's conservation of mass in that object, probably. And if you have some data points, you're going to try and predict things about the sun. Your neural net doesn't care about conservation of mass just by itself. So no doubt about it, you have to embed the physics that we believe is true inside of those things. Yeah. So now we're back to supervised methods. But I also think unsupervised tools will be very interesting on the horizon. But I think we should probably go to the next people so we can hit everybody, right? I don't want to take everybody's time.
Okay, I don't know if Christina is on the Zoom, but we have our other.
I think Christina said that she wouldn't be on the Zoom because she had a meeting at this time. So I first wanted to say that for me, this meeting was great just because I got to listen to research on areas that I could get some kind of a feel for because they had some relation to things I knew and yet weren't what I normally work on. So it's been a great pleasure. About turbulence in active fluids, I guess it's reasonable to say that something like turbulence sets in active fluids because active fluids are chronically prone to physically interesting instabilities. And because they're set in a fluid dynamical setting, you do get complex flows and eventually certain kinds of turbulence. It's a pity that Luca Jomi, I guess Luca is not here, right? Yeah, it's a pity Luca Jomi is not here because I guess of the work presented on the active matter side, his was probably the one that is closest to turbulence, vorticity, and so forth. So from my point of view, I thought one thing that at least people in my field could take away from this conference is that turbulence as a subject has been around for a long time in a variety of contexts. There are certain kinds of hydrodynamic turbulence, MHD turbulence, for example, whose equations look not very different from the kinds of equations that we write down for instabilities and turbulence in oriented fluids, where the orientation field responds mechanically in ways that's very similar to the magnetic field, where there are wave-like modes at long wavelength which look an awful lot like Alfvén waves. There's probably some things that our game can learn from that kind of turbulence. The other thing I wanted to say is that historically, complex fluids have also served as mini laboratories in which to produce phenomena with some connections to astrophysics, like the defect coarsening story in liquid crystals and its similarity to cosmological defect formation. So it might be interesting to see if there are active and other soft matter problems in which long-range interactions, either phoretic or Stokesian, can be used to mimic structure formation phenomena in cosmological context, because there's inverse Laplacians of many kinds in those contexts. Apart from that, I guess I don't have very much to say other than that clearly active turbulence is a sort of relatively new entrant to the turbulence game. It has some features similar to regular turbulence. It lacks some features. It'd be interesting to see if we can push active turbulence to the point where one asks the more advanced kinds of questions about structure functions and so forth that we've seen in mainstream turbulence.
I had a question
Yeah.
on that, and so the Reynolds numbers seem to vary greatly in the active turbulence systems, but typically were low.
They're all zero.
Essentially, all active turbulence problems.
Well, no, but you had
Yes.
some orders of magnitude, but all low, right? So
Yeah,
I'm just
so you should pretend they're zero, except in my talk, what I talked about is taking active hydrodynamics models and entering the regime where inertia matters a little bit, and then seeing what happens. Even if you do, you'll never be at. Okay, it's true that if
the point I wanted to make is that while the Reynolds number is like the key, like what I see like difference in terms of like the astrophysical and geosystems and the active turbulence systems is the Reynolds number is totally different. The structures you see are somewhat similar, right?
Yeah,
so I think that's maybe an interesting key point to look at in terms of the statistics, right? Like even though you have vastly different Reynolds numbers, is there still some universal types of statistics that these systems exhibit with the high Reynolds number systems?
Well, I think the velocity, if you measure, first of all, in the kinds of problems we've talked about, the velocity field doesn't have a dynamics. You can treat it as instantaneous action at a distance, determining the velocity everywhere by the force fields everywhere through the Stokes equation. Therefore, the velocity is actually obeying the other fields which are doing the driving. So even if you measure velocity structure functions, you're actually just convoluting in the Stokesian propagator to determine the velocity in terms of the other fields in the problem. So what you should think of, I think things like the vortex statistics that Luca talked about are, size distributions and so forth are probably a more appropriate thing. You are not going to get huge, V of x minus Vx prime scaling as x minus x prime to some giant, big power, those things. I don't think that's the kind of thing you would look at in this context. That's my feeling. On the other hand, if you're in a system in which the orientation field, for instance, is in ordered phase, the transverse fluctuations of that can have structure functions which scale with distance because you've broken a continuous invariance, and now you have a variable whose structure function can scale. So there might be structure functions of other quantities akin to other turbulence-like problems like Kuramata-Sevashinsky or something. There are analogs of that sort. I don't know if I answered the question or somebody else's question.
Maybe I can just make just a technical comment on the Reynolds number at low Reynolds number. Is that when you go into low Reynolds number, that's actually a regular perturbation from zero, so to speak. And so you can do an asymptotics where you expand around, Reynolds number equal to zero and powers of Reynolds number, as long as you're in a finite system size. And so you don't have this problem like at high Reynolds number where you take Reynolds number off to infinity.
Right, and that's singular.
And you can't pretend as though you just got rid of viscosity altogether because it's still producing things, shear flows off of boundaries and things like that.
Reynolds number regime, we're not entirely sure how things scale as you go to, 10, a greater than 10 to the 5 or 10 to the 6, right? Because the simulations can't get there, and then the experiments have trouble in terms of boundaries.
The only point I'm making is that end of things is more controlled when you're taking the Reynolds number to zero. It's not like taking the Reynolds number to infinity.
Yeah, I just remember seeing like 10 to minus 3, 10 to minus 4 in some of the slides.
Yeah,
but maybe that's
think of
them as zero.
Yeah,
think of them as zero. Just putting the number up there to show you that
there's a number you can measure
and
it's really small. Yeah. So, another point I alluded to is that there are some systems actually that map almost exactly onto some classical problems. And so, for example, if you just take a set of rotors, so you take particles in a Stokes fluid and you drive them by an external torque, right? Just a little sphere, you drive it around. That's like a vortex, kind of, right? So imagine you take a whole plane of them and you hold them in a plane in a fluid. And you do some sort of mean field limit and you look at the velocity field that gets produced by that. That's SQG. That turns out to be exactly semi-quasi-geostrophy. And there's other types of variants where, so that's more of a geophysical analog. And, or if you take a bunch of particles that are rotating in a membrane, it turns out that locally, if you take their far field interactions and kind of treat it that way, it turns out locally that looks like Euler. And then when you go far away, it looks like SQG. So there are these weird systems that map onto kind of classical, more Hamiltonian-like ideal fluid systems that exist at the zero Reynolds number limit, and they arise because you have an exact balance between dissipation and drive. And that balance is exact, and it gives you Hamiltonian structures that you just would not expect necessarily. So I think there's some places where you're looking at more than just kind of analogous behaviors, but there will be difference in the way boundary conditions come in and things like that. But yes.
So sorry to back to a different issue, but just I picked up on it and didn't want it to get lost.
But mine was so fascinating.
Well, it was, and I'm sure mine will only fall short of that. But much like you suggested, we take a series in inverse Reynolds number. I'd like to, invert your comment and say something about the inverse Laplacians. So, Sriram, I was pretty shocked that you mentioned that because that is actually a huge issue in cosmological perturbation theory. Basically, when you do Feynman diagrams for the higher order corrections to things like the power spectrum of large scale structure, you do end up with these inverse Laplacians, and you basically get absolute values of sums of momenta that you have to integrate over, and you can't really factorize 1 over q1 plus q2 plus q3 plus q4 if they're all vectors. If they weren't, you could maybe use partial fractions, and that's actually led to a whole area of research in cosmology about dealing with these inverse Laplacians, so you don't have to do 16-dimensional integrals to compute these corrections. So if people in fluid dynamics are dealing with these things and have ideas about that, I think that would actually be pretty
Mike
welcome.
might have more of an answer, but I mean, the simplest context in which it comes up in low Reynolds number fluid dynamics is if you've got a bunch of particles settling in a viscous fluid, then if you ignore inertia, each one has a velocity field that decays as 1 over distance, and they start clumping. And that clearly has features similar to structure formation in gravitating systems. But I don't know about the particular technical issue that you brought up. What the ultimate state of a collection of Stokesian sedimenting particles is probably still not a settled issue. No pun intended, sorry.
It's a settling issue.
But there's also others. I mean, the point is that if you've got particles that on the surface of which a chemical reaction takes place, which propels them, then the diffusing species of that chemical reaction gives you another thing governed by a Laplacian. So the interaction between two such particles can have inverse Laplacians. But I don't know about the point you brought up. I just don't know.
Maybe I'll make one remark. And when you're looking at an active fluid that sits above another fluid, which is a very common situation. So in Zonemir's experiments, you have an active fluid layer that sits above essentially an infinite viscous fluid. So you have a weird problem where you're inverting stress through a lower fluid up into a velocity on the surface. And that's usually kind of an elliptic problem. But it turns out that kind of filtering from surface to surface, so it's kind of Neumann to Dirichlet from surface to surface, that gives you the natural invertible thing is not the Laplacian, it's actually the square root of the minus Laplacian. And so there's kind of places where you can kind of change the order of the elliptic operators because you're kind of filtering through external media. And so maybe that's something to do with what you're saying, I'm not sure, but yeah.
QGs, Helmholtz, the Lagrange Laplacian, Helmholtz operator. You can. Oh, sorry. So QG, which stands for quasi-geostrophic, the inversion operator is not a Laplacian, but a Helmholtz. And SQG, it's some other power. So you can invent, as an applied math problem, all kinds of funky fluids with different types of inversion. Yeah, and people have. And what it amounts to is adjusting the interaction length or the screening effect between the structures.
Just one remark regarding your question. I don't remember exactly why, but in the simulation, when you talk Reynolds 10 to minus 4, I think it's a mistake to assimilate 10 to minus 4 to 0, because the two things are very different. At least in the numerical practice, it helps a lot to keep the nonlinear term alive, even if it is 10 to minus 4. Now, if you ask me why, I cannot now recover the argument, but I know there is one. So I wonder whether this could help in regularizing.
That's why I qualified my statement about not having infinitely large systems, because there is so seen breakdown of Stokes.
Yeah.
But if you have a finite system, then you have a nice clean asymptotics. It's not clean if you have an infinite system.
Right.
Inertial effects
But you're talking strictly the Stokes problem, where Reynolds is plane zero. Did I understand correctly? Yeah. All I'm saying is that in the real life, most of your experiment, and for that matter, in many of the problems I'm dealing with in soft matter now, Reynolds is 10 to minus 4. In the numerics, we know for a fact that keeping U grad U, the inertia alive, helps a lot. And Tony Ladd, who is a colleague in Florida, once gave me the point, the reason I cannot reconstruct, but it was a very cogent point, that that term has to be there. I'm talking now numerics.
Is that just the Ozine correction or something else?
Well, it could. Let's say that the nonlinearity could help regularizing the infinities.
I think we're talking about stability.
I think so. I think so. I think that.
Yeah, but let me just make one. Yeah. One reason not to keep it, if we're talking about numerics and you're dealing with a homogeneous Stokes problem, is that you can move to a boundary integral formulation of the problem, and you can go to far greater complexity in describing the geometry. Just a different, completely.
I was picking up on this remark with the analogy with the Feynman, the problem they have because I heard this discussion from a different colleague, so there must be a connection. The second point is a question regarding, again, Reynolds. It was really delightful to learn about active turbulence. I think there is no shame in using the word turbulence because there are many turbulences, okay? Hydrodynamic is one, is probably the dominant, but it's not the only one. Now, seems to me that you don't have Reynolds, but you must have some other number which justifies a spectrum in length scale. And I think I raised this question before. So, and then I think it would be very interesting to see what this different kind of linearity is bringing up, and it would be a different form of turbulence. Period.
So as one example, which is not the active part, but is elastic turbulence, the analogous parameter is the Weisenberg number.
Right. Yeah. So there must be an analog.
Sits against the convective term for the stress advection.
So the point is having some scale separation and a nonlinear mechanism to feed the cascade somehow. And it doesn't have to be necessarily Reynolds. That is my very superficial reading after what I learned.
Sandra, do you want to?
So I just wrote the simple equation this morning, and it's just showing that the nonlinearities, the magnitude of the nonlinearities given by the Weisenberg number in that case. So yeah, there is some number, dimensionless number that can be used. Yeah, right.
Small point, which is that in the active problem, in fact, it's not even a comparison between a nonlinear term and a relaxation term. It's actually two time scales, the orientational relaxation compared to a time scale that comes out of the active stress divided by the viscosity. So it's not even a comparison between nonlinear and linear. It's already there in the linear theory. And it's that whose growth makes the problem, makes nonlinearity in the problem important. Yeah. Yeah. So, but the relevant comparison turns out to be between quantities determinable in the linear theory.
Okay, so we'll move on to 5. It was fantastic for me to see in how many different physical contexts the Taylor-Couette flow appeared. Right, such a simple setup that has such a historical significance is popping up in active matter in the experiments and then in the astrophysical context. So I think Hubert brought it up in terms of the circumstellar disks, but maybe you want to lead the discussion on the importance of these rotating systems. Just, informally. If you want to come to the front, or you can stay there, yeah.
So one thing which I found really interesting here was that some people talk to me about real turbulence and not so much real turbulence, and that people are still hoping to find one day real turbulence in a protoplanetary disk, what they would then call like the nonlinear case for the Taylor-Couette experiment. So this was really interesting, and I think this is something the community is now dealing with, where this would actually have consequences. So whether turbulence would eventually be much stronger than before, or just have different characteristics in what we want to find. So, but otherwise we are happy that the protoplanetary disk is probably just like a weather system. So really strongly convection driven and temperature gradient. So. One of the problems, of course, we have also already in analyzing our simulations is that we are so horribly, stratified, and this is just a huge mess. And therefore, I hope then also to get better. I got some feedback here, so to get better analyzing tools for these kind of instabilities.
I actually had a question for James and for some of the other speakers yesterday. Doing these rotating systems with these zonal jet flows that are up here. I mean, in your case, you found the zonal flows merged, and the Daedalus simulations, they don't find that. What is the difference between the simulations where you see merging and where you don't see merging? Is it temperature? Timescale, okay.
Yeah, well, their simulation is horizontally non-divergent, so it's a it's 2D incompressible system. And the equations that I saw has finite interaction length. It's a horizontally compressible system. So what that does is if you form structures in your fluid and you wait long enough, in their system, that they eventually know about the existence of the other structure, and they'll interact. Whereas in the shallow water case, in the compressible case, if it's outside, if two structures are outside the interaction length distance, they will persist and they can remain for a long time. Okay. Did that answer your question?
Actually, there is another element to this. There is a difference if the flow is forced or unforced. In forced flow, the jets tend to stay separate from each other, and this is it follows from turbulence properties. And if it's unforced, then you will get merging of the jets. It also depends on other parameters, but the flow regimes are very different, forced and unforced.
I think this effect of stratification is very important. In astrophysical system, it's almost always the gravitationally stratified atmosphere in galaxy formation or structure formation of protoplanetary disks. In many of the galaxy formation simulations, that this effect of sedimentation is not taken into. Usually we assume single fluid approximations. We just have one fluid, and then we'll follow hydrodynamics usually. So I think this is a bit of an underdeveloped field. But we heard a very nice talk from Shumel, I guess, about how to probe ISM turbulence using chemical elements with multi-species. So it is. I think that's the kind of area where the effector stratification has to be taken into account. How different, the chemical elements with different masses will be, tracing each other, not just the same, but how differently they are tracing. So we're probably probing different aspects of ISM turbulence, and I don't think there's like a very nice models of that that takes all of this effect into account, but the observations are there to be interpreted. So maybe I think that's one area that's important. I encountered the same situations in galaxy clusters where we have hydrogen and helium plasma, and if you wait long enough, the heavier nuclei like helium will just sediment into the central regions eventually, so there'll be component separation. But there, we know there's a turbulence. So my question here, that maybe to the audience, is how do we model the effect of sedimentation and how the turbulence how the particle interact with the turbulent medium in this sedimentation process? Do we have a approach, the way to do this? How, in presence of turbulence, would the particle sedimentation speed, how would that be affected? Do we have a well-defined way of modeling the effect of particle sedimentation in presence of turbulent medium? And if there's a mechanism for that, I think that's something that we really need to get our grasp on if we were to interpret things like ISM turbulence using multi-chemical species. It's more
So the interstellar medium is a good example for the least stratified situation you can have in astronomy. So this is really gentle. A case where things are dealt with, what you say, is then also done, for instance, in explosions. So supernova explosions, when you then have your flagration front, and then you need then the proper transport of burning material into this one. And then, of course, your numerical scheme does not provide this transport sufficiently, and they are using then things like Smagorinsky viscosity in order to see how things are being accelerated in there. But this is actually the problem. So the stratification we have in our disk is not just affecting sedimentation, it's also a stratification which is on the same scales as your integral scale of turbulence is. So, and this makes it then really difficult to, for instance, then to construct a subgrid model. So where you want then to separate things. So if we would naively use a Smagorinsky model, then it would see, oh, there is shear, wonderful, and then produce a lot of viscosity potentially locally, and this might be wrong. But then, maybe then machine learning is something which can help us to get a better subgrid model, because we are now getting into a regime where our simulations are well enough that it might be worthwhile to have additional dissipation and what you say, influence on the transport of chemical tracers and dust stuff, which so far we can't do because our crappy numerical scheme, by being just third order at most, is just the best subgrid scheme we can have right now.
The last one was Boris wanted to talk about anisotropic turbulence.
My experience when I was talking about this was mostly from geophysical flows. Probably the good example was that sometimes people, it's important to look on one-dimensional spectra, not only three-dimensional spectra in all problems. And the good example was a paper by Peter Reines in '75 on beta plane turbulence, in which he said that from dimensional considerations, when you have a beta effect, you can develop a spectrum beta square k to -5, and k was a three-dimensional vector. And he said it cannot exist because with such a steep spectrum, the energy will be concentrating on small scales, on large scale, small wave numbers. And it will affect the rest of the spectrum, so it will destroy the spectrum eventually. So not considering one-dimensional spectrum was destroying the argument. However, if you look on one-dimensional spectrum on the sphere or on beta plane turbulence, in one dimension it can go like k to -5, and it does do it, but in other direction it goes like Kolmogorov. So if you don't look on one-dimensional spectra in anisotropic turbulence, you cannot treat it properly. Now, other elements of anisotropic turbulence was in studies of oceanic turbulence, which I was showing yesterday. The spectra now, well, the new tools which are available with satellite altimetry and ship track data, they usually measure in the direction of satellite trajectory or in direction of the ship track. And they measure directional spectra. And it's luckily this turbulence is horizontally isotropic, so it appears to be the same in all directions. But if you have some anisotropy in the field, again, it's important to look on anisotropic spectra and not integrate it over the circle. And another point which I wanted to make in turbulence, but it's not anisotropic, it's just turbulence which has two different spectra. And I'm going back to satellite altimetry again. There is a lot of papers published there on spectra in oceanic turbulence, and they measure various slopes. They can get minus 2.5 or minus 2.6 or minus 2.7, and they don't go beyond the slope. And measuring the slope normally doesn't tell you much about the spectrum. What is really important is the amplitude. You need to see, I think the physics of the spectra is in the amplitude and not in the slope. In this case, as I showed yesterday, we have Kolmogorov part and steeper part, which is determined by Coriolis parameter, and they affect each other. And if you just take a point somewhere, you don't know what gives a big contribution to this point. Is it coming from Kolmogorov part or from the steep part? But if you compare the whole amplitude for different wave numbers, then you can learn much more from the spectrum. And I think this is general conclusion which goes beyond application in geophysical fluid dynamics.
Yeah, I think this topic, anisotropic turbulence, it's so rich because from my point of view, I always think of anisotropic turbulence in the MHD context, where you have various different cascades you have a perpendicular cascade, and then you have a different scaling in the parallel direction to the magnetic field. And there the spectral slope actually does tell you something about, what regime you're in terms of strong versus weak turbulence. And I was totally unaware actually of anisotropic turbulence in these other contexts. And we saw, this morning a nice talk from James, showing how one can get anisotropic measurements from the observations, astrophysical observations, again in this context of the MHD. And so I think anisotropic turbulence is, a very, very rich topic that deserves a lot more attention. Yes. Does anyone else want to comment? Yeah, Zach?
Because in cosmology, anisotropy is a big thing we have too, because redshift space distortions, which are basically distortions in large-scale clustering due to measuring the positions differently along the line of sight, those are huge, and they can give you a lot of information, but they can also screw things up if you don't account for them. So there are a lot of large-scale structure algorithms that specifically are tailored to anisotropy, and I think it would be nice to see more crosstalk between the turbulence community and large-scale structure people to figure out which of those algorithms can be used, and also maybe if turbulence people have ideas for other analyses to do that we should be doing. No, what we do is we define a line of sight and take multiple moments of the power spectrum with respect to angle to the line of sight. So in a turbulent box, if you had a magnetic field along your z-axis, you could say that'll be my kind of preferred direction, and I'll take my power spectrum as a function of k, but also of mu, where mu is the cosine. That would be one example. People do use Minkowski functionals in cosmology, but those are spherically averaged, so they don't actually trace. But I haven't heard of Minkowski tensors. What are those? Maybe we should use this.
Okay, so I'd like to thank everyone for contributing to the discussion. Let's thank all the leaders again. And on the note of thank yous, I'd like to thank everyone for coming here, for participating, for sharing all your exciting research. The talks are going to be, I think, put on YouTube, and the Dropbox will be active. So if you don't want your slides on the Dropbox, just let us know. We'll take them down. Otherwise, I think we can constantly revisit these talks and learn a lot more. And I also wanted to thank, we can see if they're out here, Camille and Melanie. Can you guys come in? Thank you. So obviously it took a lot of work to bring all of us here together, and it wasn't just Mike, David, and I doing all the work. We had a big, big help from Camille and Melanie. And we also have a fantastic AV team that we want to thank. So Jason, come out of your control room.
Yeah, the wizard needs to come out of his box.
There he is. And with that, we'll break for lunch.
Yes.